In this video, we're going to introduce the representation of unsigned integers as bit strings, and we'll also discuss addition and subtraction within this number system. Machine integers are represented as fixed-length bit strings. For example, in C, unsigned ints are represented as bit strings of length 32, which means that there are 2 to the 32 distinct unsigned ints. But 32 bits is a bit much to draw, so for simplicity, let's suppose we're working on a hypothetical machine with 4-bit integers. Using 4 bits, we only have 2 to the 4th or 16 different bit strings. It's convenient to represent these on a number wheel as shown here. In our unsigned number system, we use these 16 bit strings to represent the 16 non-negative integers from 0 to 15. We treat each bit string as a binary number using standard positional notation. Notice that the values grow as we proceed clockwise around the circle. We can use this representation to do machine arithmetic. Suppose we want to add 2 numbers, say 4 and 5. We start at location 0 and move clockwise 4 positions, and then to add 5 to that, we simply proceed clockwise another 5 positions. And we end up at 1001, which is a representation of 9, the expected answer. Notice that we also could have simply added the 2 representations using binary arithmetic. 4 is 0100, and 5 is 0101. Now we're just going to add those. We add these using binary addition starting at the rightmost position. 0 plus 1 equals 1. 0 plus 0 equals 0. 1 plus 1 equals 2. But in the binary number system, that's 1, 0. Hence we record the 0 and carry the 1. Finally, 1 plus 0 equals 1. And we're left with 1001, or 9. So far, so good. Now suppose we wanted to add 9 and 10. Using our number wheel, we move clockwise from 0 to 9. And then we move 10 more spaces clockwise to 0011. But wait a minute, that's a 3, not 19 as we might have expected. The problem is we can't represent 19 in our 4-bit representation. All of the answers have to fit into 4 bits. Integer addition within our 4-bit system is addition modulo 16. And since 19 mod 16 equals 3, this is the right answer. Or at least it's the answer that our 4-bit machine would give us. The machine also might set the carry bit in the processor to indicate that the answer overflowed. Again, we can also compute the result using binary arithmetic on the representations. 9 is 1001, 10 is 1011. So when we add those, we get 10011. Notice that that's a 5-bit answer. But since we only have 4 bits to store the result, we have to truncate the high-order bits to yield our 4-bit answer of 0011 or 3. Notice that that's the same answer we got using our number wheel. Again, the processor might set the carry bit to indicate a carry out of the high-order position, that is, an overflow. Finally, suppose we're subtracting instead of adding. Let's compute 4 minus 5. Subtracting a number means moving that many places in the counterclockwise direction on the number wheel. We first go clockwise 4 positions, and then we go counterclockwise 5 positions to represent the subtraction of 5. That takes us to 1111, or 15. Now we'd expect 5 minus 4 to give us an answer of minus 1. But remember that unsigned addition in this system is really addition modulo 16. We can't represent minus 1 as an unsigned number, but we can represent minus 1 mod 16. That answer is 15, which is what our machine gives us. Of course, what we've said about our 4-bit integers applies as well to 32-bit or 64-bit integers.